Should I get started or should you wait a couple more minutes?
Yeah, we can wait, I think. For 1
we
minute.
can.
Yeah, we can
Okay.
start at 11:05.
Sure.
Thank you.
So is it a good time to start?
Absolutely, Morteza. Whenever you prefer, please start.
Sure. Yeah. Well, thank you everyone for joining today. Today I'm going to talk about a paper from Department of Statistics at Cornell University. The title of the paper is Bayesian Spillover graphs for dynamic networks. In this paper, they came up with a new method to measure spillovers in networks and also measure causality that does not have the restrictions and assumptions that are present in other methodologies, such as basically Bayesian networks, or basically some of the assumptions they have, such as directed acyclic graphs and things like that. So they sort of try to overcome these assumptions and also provide a good framework for measuring impacts and spillovers in a dynamic network, and also multiple time series data. So they start their paper by first talking about the new method, BSG, Bayesian spillover graphs. They talk about the new method they developed, and then they spend a good bit of time comparing this new method to previously established methods so far. And they do a comparison basically on what advantages their method has over the sort of commonly used ones so far. So they spend a lot. They spend a little bit of time talking about that, and then they dive deeper into the approach and methodology, how they were able to come up with this new method, what is the theory behind it, and what are the sort of the calculations and how they derived this method. So they spend a little bit of time talking about that, about the matrices and different equations. And then they come up with some new measures, such as H spillover index, to sort of measure the effectiveness of their network, or the spillover effect. And they talk about that a little bit more, and some other sort of variables that they introduce, such as vulnerability score in the network, and then influence score in the network. So they spend a little bit of time talking about these new measures that they could come up with. And then they sort of, at the end of the methodology section, they talk about an algorithm they use to sort of derive samples from the posterior distribution and make some computations, and they sort of walk through how they can measure the impact or the spillovers in their graph. In the third section of their paper, they talk about sort of such as basically an example using synthetic data. They try to generate some sort of graphs and try to show this the spillover effects in different horizons, basically. And they sort of, with their synthetic data, they try to illustrate how this mechanism basically works and show basically the effectiveness of it in comparison to previous models. And after they do that, they have a table that shows the accuracy of basically measuring that spillover effects or identifying the sink and source nodes. So they do that, and they sort of try to measure accuracy as well for different time horizons. And after they do this on the synthetic data, they sort of show an application of this on a real world example, which is a California wildfire in 2019. And for different counties in California, they sort of illustrate that basically how this model can be applied to the data set, to this time series data set, because, and we're gonna get to this a little bit more, but the wildfire in 2019 started from early October until end of November. So it was almost a 2 months ongoing scenario. So this was a time series, constant time series, and they had a sort of a measurements they used to sort of measure the intensity of the wildfire, and they have that measurement for different counties. And what they do is that they apply their model on different counties in California to sort of try to identify which of these county basically was the source node, and which ones were the vulnerable nodes or sunk nodes, and also to measure the spillover effects between these counties. So, and at the end, they talk about how effective this approach is to identify basically if firefighters want to start putting out the fire, which county to start with, because for example in this case this Sonoma County seems to be the source and has indirect spillover effects on all other counties. And this approach is something that is not present in previous approaches, and this spillover effect is something that they were able to come up with basically in this paper. So yes,
may I suggest one thing? If you could do
sure.
that would be best. I would like you, if you could explain to us this type of graph, because I assume that many of us are not familiar with this particular type of graph, right? So maybe define, and also like in what type of application scenario, what kind of analysis these type of graph would be useful.
Sure, definitely. And
so
I have some.
We get understanding what it is, and then later on go into detail of this.
Definitely, I will do my best, and I have some examples. I have some of the basically some web pages here I can pull up and go a little bit deeper into this. So basically, what the type of graph they use here is a dynamic, basically Bayesian network. And what basically this the approach they have, it can be applied to any network that is time series. And in this time series network, for example, this California wildfire, there are shocks that becomes applied to the whole network. For example, there is a network, for example, let's say we have a time series data set for about 20 years, and then different shocks happen to all these basically data points or nodes in the network. And let's say COVID being an example of the shock, and the nodes being different countries around the world, and the time series would be from when the COVID started until now, for example. So what their approach is that basically when a shock happens to a network, they want to measure the spillover effects of basically the impact of different nodes on one another, and also how vulnerable each node is to this shock, because the vulnerability is not the same for all of the nodes in the network. And one example I have here, which I wanted to basically bring up a little bit later in the paper, this is the dynamic Bayesian network, which is there is a network basically there are nodes that are connected to one another, and because it is a Bayesian network, we have directed basically edges, which means there is causality between different nodes. There are different factors that basically cause each other. In the California examples, these nodes are counties that they sort of pass on the fire to one another, and then there are different time steps that this network is being basically looked at, or we have data for. So this is the type of network that they primarily focus on. And what they say in the paper, their claim is that the Bayesian network approach is a special case of this basically dynamic Bayesian network. What they say is that the Bayesian network approach, which is used by Pearl, which is introduced by Pearl and others, that is the stationary case of this sort of general approach. So they try to say that they have a more general model for networks that basically is over various time points and is a time series approach to looking at the networks.
Thanks. I would like to ask another relevant question.
Sure.
And maybe Zona might be familiar with this type of graphs, but I would like to, in particular, understand if you know, like contrast dynamic causal models. I send a link to the chat. With this type of, I hear background noise.
It's not on my side.
Yeah, so basically, if you could contrast these two and how we can reason about it, and in particular, I'm asking this because for some of us that we may want to choose one type of, graph models for any analysis that is relevant to our research, how we can go after it, right?
Sure.
If our choices are these two.
Definitely.
Or maybe like these two type of graph are basically equivalent. I don't know, but you guys may know.
Yes, definitely. What I can say to that is that this dynamic causal model or any I think this dynamic causal modeling is not about network necessarily, meaning we don't have a fixed set of nodes that we are observing over time. In the California example, there are fixed number of counties that we observe over time, and they have interactions with one another. That may not be the case always. So in this paper, they focus on networks specifically. So that is one thing they basically have on networks. Another thing that I can say is that this approach in this paper is when we are interested in spillovers and impact of nodes on one another over time. Basically, I would say cumulative impacts that nodes have over time, which cannot be measured in a stationary phase. So I think there are three things that will separate this paper from other approaches. One is that this is a time series approach, so we cannot really look at the stationary data and basically apply this approach. So we need to have continuous data over time. So this is one thing. Another thing, we need to have a network of basically nodes, and we would be interested in basically what are the influential nodes, or what are the sunk nodes and things like that. And another thing is that we would be interested in a spillover, and this spillover is that and they talk about in the paper, it is not an edge between two nodes. It is an indirect edge that is hidden, but we identify that over time. And what they actually have here, I think this can be a good example. Over here with the synthetic data, they have 5 nodes, and there are some basically edges between the nodes, which are the causal nodes. And this is at only one time point, but they repeat this experiment over and over, and they 10 time periods over, they see this red sort of edge, which is not a direct edge. This is called a spillover edge, meaning this is a cumulative effect that node 3 indirectly has on node 5, meaning the changes in node 5 over time is not coming directly from node 4, but comes from node 3, and they can identify that using this approach. And one other thing I can say about this paper is that they use a Bayesian approach, which in most cases it is similar to other papers. So this is not very distinctive of this one. I hope I was able to just give a very overview explanation of what they try to accomplish in this paper. Are there any other questions or anything else I can elaborate first?
Thank you.
Thanks. Is like I would like others to ask their question because there should be so many questions about this. And thanks for great explanation.
Sure.
So
One.
to repeat this, can I say that, like, let's say this type of graph capture the temporal aspect of the interaction between variables, right?
Exactly.
Instead of like the instance like effective or causal effect of variables to each other, right? It still might be causal, but causal in a sense of the temporal aspect, right?
Exactly.
But also note that the dynamic causal models also have this kind of a sense too, so maybe like one, if anyone came across any example or tutorial with contrast with respect to two different analyses, these two type of graph, that would be awesome. But sorry.
I would like to comment, I think for dynamic causal models and dynamic networks, these dynamic causal models are taking into account the dynamical equations and which are actually associated with nodes. So basically we have a network which is interconnection of multiple nodes, and each node will have its own dynamics. So in this case, I think for Bayesian networks, are we considering the dynamical equations for that, for individual node involved into the network?
It's not at the node level, it's at the network level. So they
so
they apply the Bayesian for the whole network.
Whole network, yeah. So that's the main difference I think I can see right now from DCM and dynamic Bayesian networks that are presented here.
Thanks, Sonam. So basically, you're saying that one basically have this, dynamic equation that govern node-based interaction. Another one is capturing graph level in
right.
evolution,
So
right?
basically, if we can relate it to causal models, it's like we have causal model which is graphical. We talk only about graph, causal graph, and other is we talk about a structural equation model of it. So even we have kind of equation associated with it, which basically talk about the effect of one particular variable on other and its contribution. But in graph, what we talk about is like only the cause and effect. So which particular variable is causing the effect on other variables. So that's only the thing that we can understand from it. So basically, there are two ways which we are talking about. So network level here. So network is basically, if we talk about complex network, it has multiple nodes, and each node has its own dynamics associated. And there will be interaction between each node and what kind of data is shared between those. Like there could be some variables which are shared, and how this network as a whole changes with time is nothing but the dynamical aspect, temporal aspect that we are talking about. If this particular network is it changing over time? Is it constant over the time? And how does it affect, the temporal aspect comes into picture in this way, I think.
Thanks. I love this explanation. Thanks, Sonam.
Thank you very much, Sonam. And this spillover effect is something that they really focus on in this paper, and I think I hope I would be able to explain this a little bit more as we get to the paper, which as is illustrated in this figure, it is not a direct edge and not easy to find and see using other approaches, but using this Bayesian approach, they want to say that indirect effect that the nodes have on one another is important. And as I mentioned, the application of that is, for example, in this California example, these blue edges are the direct edges, that basically meaning the fire went from this county to this county and this county to this county, and this is directly observed. But over time, over the course of 2 months, there are indirect impacts of basically fire from this county to the remaining counties, and they were able to first of all measure that impact and also identify the nodes. And so this county being the basically having the highest influential score, as they say in the paper. And for example, I think there was one other county, I think it's this one, that is the most vulnerable node in the network. So this spillover thing is another thing that they mentioned they have not seen in other prior basically methodologies that they introduce here. Are there any other questions? Otherwise, we can take a look at how they explained their approach in the paper.
May I have a comment about the dynamic Bayesian networks?
Sure.
Are they claim that these dynamic Bayesian networks are causal in this paper, or their intention is to have a causal interpretation of these type of network?
I think what they claim is not that these are causal. They don't necessarily say that, but in like the graphs, they have like all the edges are directed, and also they use the sort of the Bayesian probabilistic approach to measure the edges. So I think that is an output of their methodology, that it is causal, but they don't focus on that. They are more interested in spillover effects and measuring some scores from the network, if that makes sense. So basically, I think they have a more general approach. They say their approach can work for both causal and non-causal networks, but the output works for basically all the networks.
Mohammed, thanks for this interesting question. I would refer to explanation on page page 2 on the left-hand column, the last paragraph. We emphasize the distinction between Bayesian DAG versus BSG, which models temporal bidirectional relationship that can potentially amplify spillovers over multi-step horizon. Right? DAG structure is the popular assumption in causal inference and can be viewed as a special case of BSG. Right? So, like I would say, since it's focused mainly on bidirectional, relations, it wouldn't be appropriate for the usual causal analysis where we would like to estimate the causal effects, right? So but if you would like to do analysis which have some temporal aspect, then this would be a good type of models, I would say.
Yeah, because based on my understanding of Bayesian networks, each causal Bayesian network is a Bayesian network, but not vice versa. So
that's right.
Bayesian networks is a more general framework for probabilistic reasoning. So doesn't mean that each Bayesian network has causal interpretation. And simply a dynamic Bayesian network consists of a time slice. And this time slice is a one shot of the model that repeats during the time. And this time slice is a Bayesian network. This Bayesian network doesn't mean that has a causal interpretation all the time. We're just a Bayesian network. So I believe their methodology is not claiming that this has a causal interpretation.
I agree. That's right. They yeah, and they say they have a more general approach. It can be causal, and as they say, DAG is basically a special case of this approach. But they don't say that. A question.
My point is, even if we use only DAGs, that doesn't mean that dynamic Bayesian network is DAGs is causal.
I see.
But again, it's not true that any Bayesian network is a causal structure, causal model. It's the other way around.
Yeah.
A causal model can be viewed as a causal Bayesian network, but not vice versa.
Makes sense.
Thank you.
Sure. Are there any other questions, or otherwise we can get started and briefly go over the basically different sections of the paper together.
Excuse me. What do you mean about vulnerability of a node? It's vulnerable to eliminate during the time?
Yeah, I think that's a great question. So what this is something that they come up with, then they call it vulnerability score and influence score. And what this is that assuming we have a network and basically it's a dynamic network, so we are observing it over time, and there is a shock that is applied to this network. There are some nodes that are more basically more impacted by that shock, and they have a measurement for that. They call that vulnerability score. And there are some nodes that basically after this shock happens, they influence other nodes more, and they call that influence score. So vulnerability score is not basically a measurement that this node is going to be removed from the network or something like that. It's just a measurement of how vulnerable or how much basically change it will observe from other nodes in the network.
Thank you.
Sure. And they talk about how they basically derive the equations and how they come up with this approach with some simple sort of steps. So basically, what just an overview on their approach to derivation of this methodology in the time we have is that they use basically forecast error variance decomposition, FEVD, and we can talk about this a little bit more. This is a variance autoregressive approach that is established basically previously. It is and they show the equations, and they talk about it a little bit more, which helps in uncertainty quantification via Bayesian time series models. So they use this approach basically to come up with different measurements we have. They come up with. So one of the measurements they come up with for a network, for a dynamic network, is H influence index, and H being the horizon hyperparameter, meaning what time slices or what time intervals we are looking at the network. And they talk about that a little bit more. And as I mentioned, they perform some experiments to show what nodes are being the source nodes, which ones are being the sink nodes, and things like that. So after they introduce their method, which can be applied to multivariate time series data, they start their paper by comparing that to granular causality or network granular causality, which is a established method in sort of basically time series causality in a time series situation. And I think I have the, if not the paper, I have the some explanation about this, about granular causality. This is a very important sort of explanation about the approach, and this has been used so far in basically measuring causality over time in a time series situation. And network granular causality is an extension of this approach to a network. So when we have a network and it is still a time series situation, and they after they introduce the network granular causality and explain that a little bit, they talk about different vector autoregression models, VAR models, and these basically these vector autoregression models have been used to measure that impact between nodes in a network. So they talk about that a little bit, and they also talk about Bayesian networks and dynamic Bayesian networks, and the reference papers where they were initially introduced. And then they talk about the sort of various methods for estimating network granular causality, adjacency matrices, meaning the impact between nodes in a time series network, what methods have been used so far in order to basically measure that impact or a spillover, for lack of the better word. There are various methods that has been used: statistical recurrent units, sparse RNNs, or self-explaining neural networks and things like that. And some of these approaches they do use in their experimentation to compare the accuracy of their own method based in the spillover graphs to all these basically methods used so far, and they show higher accuracy in basically better results from their approach. So they do a comparison study as well. And then one other thing they talk about is that basically for this network granular causality, and as I mentioned, this is a term for measuring causal impacts over time in a network. So they say if we want to use DAG for basically measuring or estimating these measurements, these would not be necessarily true representative of the network interactions, because sometimes the nodes can be self-directed, and sometimes they can be bidirectional, or they can be cyclic over time. So we cannot really limit ourselves to just focusing on DAGs, because we're not basically allowed to have cycles in a DAG structure. But sometimes in a real world scenario, we may have cyclic basically networks over time, or sometimes the node may be self-directed, or sometimes they may be bidirectional. So they say that there are assumptions in a DAG approach that sometimes that sort of limits our ability to measure impacts in these NGC or network granular causality frameworks. And after that they talk about they sort of summarize major drawbacks of other approaches. So they introduce basically 3 points as what are the limitations of the current approach. One of them they say is lack of flexibility for observing network interactions over multiple forecast horizons. And these observing network interactions is what they later call a spillover effect, which are not direct edges between sort of nodes, but cumulative interactions or spillovers that occur. That is one thing. Another one, lack of interpretable network measures that are contextualized, meaning these interpretable network measures. One of them is that vulnerability score. Another one is influence score. Another one is influence index that they introduced, that sort of these are the measurements on a network that can be helpful, and these can be derived using this Bayesian spillover graph approach. So this is another thing. And the last one, lack of uncertainty quantification for strengths of temporal relationships and node influence. So sort of how certain we are and what is the measurement for uncertainty of the measurements over time. This is another thing that they say their model has sort of, and this can be helpful. So, and they talk about that a little bit more in the paper. So then they talk about their motivation and their approach, how their framework can be applied in a real world scenario, and how each of these sort of points, each of these three limitations of other models can be addressed using their own methodology. So they talk about that a little bit. They say we have these sort of solutions to these problems, and as Dr. Jamshidi mentioned here, they talk about how their framework can be applied and sort of comparing that with the Bayesian DAC structure. And they visually show that. Let me see if I can zoom in a little bit further here. They visually show this over here for a single realized multivariate time series, and they say, let's say this is the equation for basically the time for the time series, and they compare different approaches. One of them being this BSG, their own approach, another one this network granular causality methods, which is supposed to be a representation of all the established methods so far, or the previous methods. And they say in this approach, vector autoregression is used, and it is applied to dynamic Bayesian networks, and then generalized vector autoregression is used for estimating the adjacency metrics for this graph. And the measures that basically comes out of this approach is using this approach for a network over time. They can measure in and out degrees for a node. They can measure eigencentrality, closeness centrality, and between its centrality. And the limitations of this approach is that one of them, it is not applicable. It is only applicable to static NGC graphs, and also it does not provide uncertainty quantification of these measurements. But over here, they compare to their own approach, and they say this has these privileges. So they take a Bayesian approach to this estimation. So there is a posterior and a prior, and they also use forecast horizon, which is the time interval, basically how further in the future we want to do the prediction, or what time interval we are looking at. So, and then they establish a posterior of the basically network, and it's a Bayesian approach that they take for that. And they use the forecast error variance decomposition, or FEVC, which is a more general approach to this vector autoregression, or VAR approach. And I have let me see if I have this here. So this is the page for variance decomposition of forecast errors. It is a more general approach to VAR. If anyone is interested, they can read a little bit more about this approach here. But overall, what they say is that there are two types of measurements that they can obtain from this approach. One of them, temporal spillovers, which is the graph edges, basically what edges are basically between different nodes that accumulate over time as basically part of a spillover, and also some network level measures. And they introduce these, which is one of them, influence score and vulnerability score, and they talk about that a little bit more. They say this measures temporal relationships and spillovers over multiple forecast horizons, they have interpretable network measures, which is, for example, influence and vulnerability score. They can rank all the nodes based on these influence and vulnerability, sort of saying which node is the most vulnerable, which node has the most influence, basically, after a shock that happens to the network. And they have uncertainty quantification. And what they do after this is they talk about the methodology a little bit more, and they go into detail about basically what equations are used to come up with this approach. So they first start with a VAR model. They sort of define it this way, which is very similar to a regression problem or a regression equation, because VAR is short for variance autoregression, which definitely has the time components, and there are different variables. It is a multivariate approach. There is a coefficient involved, there is an intercept involved, and there is also an error term at the end, which is very similar to a regression equation. And then they say they use a Bayesian approach for estimating the unknown model parameters that they have in this VAR. So they construct different matrices, and they later use the likelihood function on this Bayesian approach, which they say looks this way. And further, they use a normal inverse V-short conjugate priors. So this is how the prior for this Bayesian approach looks like. Sigma being the error term for this sort of VAR approach, and then for beta, or the coefficients that we have in this equation for basically, which is the coefficient of all the adjacency matrix measurements. They have this equation as well, and then they also have equations for posterior. So they actually propose this posterior distribution. This one being the prior, this one is the posterior in their Bayesian approach, and then they make some assumptions and basically have some calculations in order to measure the model parameters. And these model parameters, the most important one being the vector of beta. And what beta is, again, is the coefficient, or it's the adjacency matrix values. And then they talk in more detail about this Bayesian spillover graphs again in more detail, and sort of they try to break it into pieces and explain each piece a little bit more in a more basically detailed way. And they talk more about this FEVD approach, which is the forecast error variance decomposition, which I think originally has been introduced by Diebold and Yilmaz in 2014, because they reference their paper a lot when they talk about this approach. And they sort of introduce this matrix of basically matrix of weights they introduced, and they say after we construct the posterior and the prior, the matrix of weights should look this way, which basically measures the amount of information of the H step ahead forecast error for variable J accounted for by innovations or exogenous shocks to variable K. So if we have a variable K and we also have a variable J, this spillover between variable J and variable K after a shock happens. And this shock, the way they use this shock is that they sort of divide the prior and posterior. So they want to say after this happened and before this happened. So the spillover between these two nodes, they sort of measure it this way. And this is where they introduce their H step ahead normalized spillover for between two nodes. So for example, between node K and node J, if I want to look H step ahead, and H being the horizon and S being the spillover, And because all these basically values are scores from 1 to 100, so they have this sort of equation for measuring that spillover effect over time. And this would not be possible if they did not take the Bayesian approach. So this is how they measure the spillover between nodes in a dynamic network. And then after they talk about that, they introduce these different network measurements. One of them, and the most important one, being the H spillover index, meaning for a dynamic network, we can have an H spillover index, which means in different time horizon or in different horizons, what is the spillover effect of this network? And the higher this the spillover effect, and they basically show that here, the higher the spillover effect, the more fragile the system is to innovations in any individual node. So any shock that happens to the network in overall, or to a node in particular, this H spillover index sort of tells us how vulnerable or how fragile the whole network is to the shock, and they sort of aggregate for the whole network each of the spillover index of the nodes, and they basically aggregate over, and they sort of come up with that measurement. After they introduce that, they talk about vulnerability score and influence score, which is basically nothing other than aggregating the H spillover effect that at the node level, and sort of they rank it. So if the H spillover effect is basically, if it's very, very high, that node becomes basically vulnerable. And if it is basically lower, it basically that node basically becomes the influential node in the network. So after they talk about these measurements at the network level, they talk about uncertainty quantification. And this is one thing that they were sort of talking about a lot, that is not present in other approaches, but it is present in this approach, which is after we construct our basically Bayesian posterior and basically Bayesian approach, what they do is that they do sampling from posterior distribution in their Bayesian framework. So they do some sampling and use algorithm 1 for estimating Bayesian spillovers. And one side effect of this algorithm 1 is also it helps them with measuring uncertainty quantification. So then in the paper, they talk about this sampling. So for example, they say they draw M posterior samples from from basically a distribution that has these parameters. And then what they explain here is that how they use this algorithm to also quantify the error or uncertainty in the measurement. So they come up with this equation that they claim sort of takes care of that. And then they talk about a stationarity and optimal basically H spillover index for equilibrium in Bayesian spillover graph. They first talk about what basically a stationary is. When can we say if a time series data set or time series framework is a stationary? And they come up with the theorem, which is all I think is very important. And they say if if we have a DAG and if 3 conditions are met, then we can say that sort of framework is a stationary. One is that if there is no component-wise autocorrelation between the nodes, and then if that DAG can be specified by strictly triangular matrix, and I think this phi1 this references to the adjacency matrix for the network. So if this can be specified by strictly triangular matrix, and also if all eigenvalues of this phi1 are 0, then we can say that is stationary. And then they use that to make some additional interpretations. Under stationarity, BSG can reliably model cumulative response functions if shocks are not persistent, and the system will return to equilibrium. So they talk about some sort of a special case of stationarity and how this framework can be used in that case. This is the algorithm and the only algorithm they use, as I said, for sort of uncertainty quantification and also BSG estimation. After they do that, they perform some experiments using synthetic data, and then they use a real world scenario or a data set to show the impact of their work. So using this synthetic data, they assume they have 5 nodes at basically step 1, and they want to observe that over time, or after 2, 5, and 10 is basically horizons, or in different time horizons, and they sort of measure the direct impact of, basically they measure a direct impact between nodes that they observe, and they sort of show that with the green arrow, and indirect or a spillover impact that may be observed between nodes over time, and they show that with the red arrow. And the way it works is that it does not directly impact, for example, in this case, node 3 does not directly impact node 5. It impacts node 5 through node 4. But what this Bayesian approach tells us is that this impact that we're seeing on node 5 is not all coming from node 4, and some of it is coming from, basically indirectly coming from node 3, and that's how they call it a spillover effect. So this should not be confused with a direct edge. This is not a direct edge. They just want to show the spillover effect over time, and it, as we see in basically different time horizons, we see that the this becomes basically like the width of this arrow becomes larger. So we see that this becomes thicker over time, meaning there's more impact. And this is another way to show this impact, saying we have node 3 and we have node 4 and node 5 in the adjacency metrics. These are the measurements we have for these, but in a typical adjacency metrics, there's no way to there's no place for node 3 to node 5 measurement because there's no direct edge. But how can we measure this spillover? And they say this Bayesian approach can take care of that. So in short, that's how they talk about it. And what this basically figure here talks about is the edge strength between basically edge strength into node 5, meaning let's say we have node 5 and there are 4 possible edges that come to it from 4 other nodes, and over time they sort of observe that. So it is pretty much, the edge strength is pretty much 0 from node 1, 2, and 3, because even from node 3 there's no direct edge. But from node 4, which is the one right next to it or adjacent to it, which is this purple line, at the initial time horizons, there's a lot of impact, or there's a lot of spillover, but over time this becomes sort of lower. But what we also see is from age 3 to 5, which is not directly related and it's not present in the adjacency metrics, there is a lot of spillovers or normalized spillovers. And as we see, this is not a direct impact, but the impact is huge compared to basically node 4 impact on node 5. So this clearly says how important this approach can be in measuring spillovers in networks. So after they do that, they sort of, using the synthetic data, also they calculate accuracy for identifying what is the sink node and what is the source node. And the sink node in this, for example, sink node is node 5, which has basically which is being impacted by other nodes, or it is the node that has the basically highest number of directed edges pointing towards it. And so this is the sink node, and source node being the node in the network that has the most number of edges coming out of it. That being that one. So identifying what is the sink node and a source node in a network, they try to basically identify that using different methodologies. These three rows are their approach, BSG approach. They compared that with VAR approach, and then with some other approach that has been present, they get very good accuracy scores in identifying what is the source and sunk node. So this is one experimentation they do, and sort of they have some accuracy measurements for different number of basically for different type of graphs. One of them being DAG, another one being directed stocklet, and also by Partey. They do that for the measurement for that one as well. They also sort of the correlation between the edges, they try to basically change that as well. The correlation between node J and K being 0.1, correlation being 0.5, and correlation being 0.9. So they do it under different situations. They still get very good accuracy scores. And at the end, as I mentioned, they have a sort of a real world example of the California wildfires, each of these nodes being counties in California in 2019 where the fire basically happened, and they show for a sink node being this one and a source node being this one, how spillovers can be measured. So I know we're out of time. I can stop here, and I hope this has been a useful presentation. If there are any questions or comments, please let me know.
It was very good presentation. Thanks.
Thank you very much. Thank you for the great questions.
Yes, I have one comment. Like I could imagine one application based on this. It is blackouts in power systems. Basically, there are power networks which are around us, and if something goes wrong at one node in the network, that basically cascade to the other nodes, and ultimately we have blackout or brownout. So where we do not have power as such. So this would be the best application of this particular strategy, because there also we need to find out the centrality of each node, and here they are using vulnerability index and influence score in order to define the centrality of node involved in the network. So one application that I can see right now is power system for this. That will be the best application.
Yeah, this is a nice thought, Sonam. Thanks for sharing. So I could also see like in systems challenges that can be addressed by this type of network and analysis over this type of network, right? For let's say one example could be the scenario where a fault appeared, and we want to find out about the root causes, right? And this fault basically have a temporal aspect to it. So basically, imagine several nodes in the system, and computer systems could produce some anomaly over time, accumulated, and result in a fault. You know what I mean? So it's not, instant kind of type of fault. Is accumulation over time, and it requires some temporal analysis, if that makes sense.
Yeah, that would be also one of the applications. Yes.
Yeah.
This is maybe it's of interest to most of you, in particular to Shahriar, whose research is on systems mostly, but also is relevant to this NASA stuff too, to some extent, for identifying root causes, etc. If some robotics faults have this type of nature. Not all of them, but some. And also, Maybe Morteza could. I would like to hear whether you thought about the application to the project that you're working on. Do you see any plans?
I have, yeah, and actually what they have in this paper, they have the code as well and a good GitHub repository. So I was thinking about applying that to, because we're also looking at causality, but I mean we do have a lot of knowledge questions, so I wasn't really sure how to apply it, because each of the nodes being the knowledge questions, or how we can, I'm still trying to figure out how we can apply that. Do you mean the vaccination research, or our the causal cost optimization?
Both actually.
Yeah.
In particular, the vaccination, but
yeah.
Keep an eye on this optimization stuff.
Sure.
I mean, at least contemplating and thinking about it would be always useful.
Definitely. Yeah, this can be an extension. For example, if our causal model is temporal, if we want to do it over time, this can be something helpful about measuring the spillovers and identifying the source and influential nodes. Definitely, it's very useful.
Yeah, thanks a lot.
Thank you, everyone. Really appreciate the great discussion.
Thank you, Morteza.
Thank you, Morteza, for a great presentation.
Thank you very much. I hope everyone has a good weekend.
You
You
too.
too, thanks.
Thank you.